I'm the CTO at Hex. If you haven't used Hex yet, we are a collaborative data workspace for teams. And among many delightful features that we've built, one of the main ones is a notebook. And I want to talk a little bit today about how we are kind of pushing the boundaries of the traditional notebook paradigm, which both enables really powerful new workflows while kind of keeping the interface that we all know and love today. So I'm going to get the clicker here. Cool. I know you all have opted into this talk, so I'm assuming that most of you have used notebooks and have potentially fairly strong feelings about them one way or the other. They can be a bit of a divisive topic. So let's just see who we have in the audience today. Who loves notebooks? I use notebooks for like everything, like word processing, data engineering. Got one in the front, got a couple in the front here. Some people with like maybe more mixed feelings about notebooks. Yeah, lots of you. And you know, you'll make me use a notebook over like my cold, dead body. All right, none of those good. Cool. We like notebooks at Hex. And then I assume you all kind of know what notebooks are. So yeah, I'm not going to spend a lot of time trying to pitch you on notebooks and why you should use them or shouldn't use them. There's probably too many sort of Twitter hot takes on that subject already. But I'm going to give you a little bit of background on how we're thinking about notebooks and then why we felt like reactivity was the right thing to build. So starting off way back, all the way back, so far back in the 1980s, Donald Knuth pioneered this concept of literate programming. This is a version of programming where you interleave the code, the outputs of the code, and narrative around that code, all in the same place. And this immediately took off. It was a big hit, particularly in data disciplines, scientific disciplines. And so just a few years later, you start to see tools popping up around this, the most famous being Mathematica. Fast forward to today, and notebooks are everywhere. People use notebooks for everything under the sun. You have your workhorses like Jupyter, but you see them in data engineering. You even see sort of more software development-centric notebooks even. So Observable.js is an example of this. And why does this happen? Why is notebooks so sticky and cool? So in addition to kind of the literate programming that I was just talking about, data analytics is just highly iterative and exploratory by nature. And the nature of a notebook to have these small modular chunks of code that you kind of run individually, you can iterate on and work really quickly on these pieces of code just made this workflow so much smoother and faster. Okay, so that's notebooks. That's why notebooks are great. But as we saw from the room, I'm sure you're all aware notebooks have some problems. This is a screenshot here from the famous or perhaps infamous Joel Grus talk from JupyterCon in 2018. I don't like notebooks. He goes through many reasons why notebooks are actually a completely terrible tool for development. And the list is extensive. I'm not going to go through all of them here, but I do find that a lot of them boil down to actually a simple fundamental problem. And this problem is so pervasive that internally at Hex, we've actually given it a name, and we call it the state problem. The simplest version of the state problem is kind of the following. Here's your really complicated notebook. You've been working on it for a really long time. Some really interesting analysis here. And then you go to run the last cell. So what does this print? Have any volunteers from the audience?
Depends on what you ran last.
Exactly. This is a trick question. There is literally no way to know what this is going to print. It could print 1, it could print 2, it could print 100,000, because this statement does not depend on anything that you currently see in the notebook. It actually depends on the contents of the memory that the notebook is running on. So if this cell had originally said a equals 15, you go and run that cell. A is now 15 in memory. You change it to be 2, and now there's just no record anywhere of what that actual value is. And the fundamental reason for this is because notebooks are built around a programming paradigm called imperative programming. And all that means is that in imperative programming, you have a list of sequential statements, you run them in order, and they update a shared mutable state. This should sound very familiar because most programming is, in fact, imperative programming. And so in the case of a notebook, statements are just cells. And then the shared memory, in this case, is actually often referred to as the kernel. But that is really just a fancy Python process running under the hood. All right, downstream effects of imperative programming models. So One of the biggest things about notebooks is that it's very, very difficult to understand what they are going to do just from reading them because of this problem that we just described. And that's true for your own notebook, let alone coming into a notebook that you don't really understand. Reproducibility, really, really important in data disciplines. But because of the way that we're operating on this mutable state that we can't really see, you can end up with these kind of really subtle bugs that make it really hard to get the same results without just like constantly restarting your notebook and running everything from scratch. But when you do that, which is actually something that we adopted at Hex here, we did this a lot. That's actually just really wasteful and not performant, because even if you're just sort of moving like a small filter or something on a chart, you have to rerun the whole big notebook, which could be hundreds of cells. It gets worse. A lot of you in the audience who have worked with notebooks probably have workarounds. You have tools, you have Jupyter extensions, you have all of these things to try to make this workflow better. But think about all of the other people in your organization who really want to work with data. They want to ask questions of the data. And they come into a notebook as their first experience with that. This can be super intimidating. It can often turn people off entirely. So not only is it making your job harder, now you also have to do everybody else's work as well, because they can't actually interact with the data in a sensible way. So where does that leave us? Notebooks are really great for iterative development, but it turns out that all of the features of notebooks that make them so great for this are exactly the same features that get you into trouble when you're trying to sort of productionize and build more complexity. And we ran into this a lot at Hex, especially once we started introducing more heavyweight SQL features, because we started getting this big influx of users who didn't even know what Jupyter was. They loved the notebook UI, but they'd never had any experience dealing with the messiness of kernel state. And so our most frequent support response to questions was, have you tried restarting and running the notebook from scratch? And that fixed like 80% of the problems. But it was really pervasive. And we banged our head against this for a really long time. We tried a lot of stuff. We ran a bunch of experiments on different ways that you could model state in a notebook. And some of them were just as complicated as the original notebook state, but we did settle on one approach that ended up being both very intuitive to users and also like really solve this sort of reproducibility and interpretability problem. So for this approach, we drew on a different programming paradigm called reactive programming, which again, I'm sure some of you in the audience are kind of familiar with this, but just to get everybody on the same page, I wanted to give a quick definition. So reactive programming is, well, if you look at Wikipedia, it says it's a programming paradigm oriented around data flows and the propagation of change. That's not particularly helpful if you're actually trying to write a program with it. So in practice, what this usually means is you actually have a set of reactive objects. And these objects maintain their dependencies up and downstream. And so when the value of one of those objects changes, it can propagate throughout the graph automatically. Why would you use this? So it has a lot of really nice properties. So we were already talking about state. Reactive programs have state consistency automatically because every change gets automatically propagated. Performance, because you are explicitly maintaining dependencies in a lot of cases, you don't need to just rerun everything just in case. You can actually only rerun the things that actually need to be updated. And then also it has some nice abstractions for asynchronous and concurrent workflows, which are really, really common in data products. This is just a quick example here of a reactive program, or an imperative program on the right here, and a reactive program on the left. So in an imperative program, all we're doing is we're sort of assigning these variables, and then when we get to here, this C, we look up A, it's 4, we look up B, it's 10. We assign C the value of 14 in memory, and where that has come from is completely lost. So when we change A, C is not updated. It's still the old value. By contrast, in the reactive side, we actually do maintain references here to A and B, and we know that that's how C is being computed. So when we update A, we actually automatically recompute C to take into account the new value of A. Normally, you'd probably be using like a library or a language feature for this, so it would look a little bit different, but I kind of left that out for ease of comparison here. This distinction might seem a little esoteric until you realize that I'm sure everybody in this room and anyone who's ever worked with data has used reactive programming before. And that's because, of course, the most famous example of reactive programming is a spreadsheet. Ahead of their time. So when you are defining a formula in a spreadsheet, you're defining a reactive node. You're defining the dependencies in the graph. And when the dependencies change, it updates automatically. Obviously, people love this. People love spreadsheets. They're never in an inconsistent state because things are propagating automatically. And it's easy to trace back the current value of a cell by just looking at the dependencies in the formula. Excel even has a feature for this. So this is the trace precedence feature, which I learned about from Barry, our resident Excel master. This shows you not only the data flow, but it also shows you another property of all reactive programs, which is that they are DAGs. Again, don't need to explain DAGs to this audience. They've kind of proliferated in the data space. And there's a reason for this, which is that they're really easy to understand, to debug, and there's really no confusion about the order in which things are being run. Cool. It's a lot of intro, but at this point, you've probably guessed what we built, which is a fully DAG-based reactive execution model for notebooks. And what this means is that when you're editing the code in the notebook, we are actually live updating the dependency graph. We're generating it, we're live updating it on top of sort of the traditional cell model. And then when you run a cell, we automatically look at all the cells up and downstream that need to be rerun, and we rerun those for you. So we found that this really elegantly solves all of the problems that we talked about earlier. So interpretability and reproducibility, because the notebook is no longer ever in an inconsistent state with memory, all of these problems just kind of go away. And then for performance, as I mentioned earlier, with the DAG, we actually can only, we can just rerun the cells that need updating and not have to worry about restarting and rerunning everything from scratch. Cool. So just to give you a quick sense for what we built here. This is Hex. And this video should play automatically in just a second. Potentially I have to click on it. Technical difficulties here. Do you know how to play the video in the deck?
Next slide.
It's okay. Let's try that. Next slide. Nope, that is the other slide. I promise this was actually a video and not just a screenshot of the product.
Maybe go add a presentation mode and run a slide. Maybe that.
Can I do that? Oh, I think I know what happened. Did we convert this to PowerPoint out of Google Slides? Because we're running in PowerPoint here. That's might have gotten lost in the transfer there. OK, cool. Well, let's go back into presentation mode then. Had to happen at some point. Cool. So basically, we're going to skip the demo. But what you will see here in this demo, or what you would have seen, is that when you go into reactive mode, essentially you have, we have sort of input parameters that we built into Hex. When you change, you can write SQL queries based on them. When you change that, automatically flows to the graph. And then we have this really nice graph UI, which I wish you could see because it's very beautiful, that shows you how all of the cells are rerunning. So cool. Let's move on and talk a little bit about how we built this. So actually, you get a nice screenshot here of this is what the graph UI actually looks like, which is pretty cool. So yeah, we have some input UI parameters here, and then all of the downstream data from that. So yeah, so under the hood, how did we actually compute this? So first the DAG, how do we create a DAG? So we explored a few different mappings here. There's a variety of different ways that you could create a DAG out of a notebook. We ended up settling on one that's pretty simple, which is just that cells are the nodes. It's worth noting that this means that reactivity doesn't work kind of within a node, within a cell rather, only between nodes. But when we kind of tested it out, we felt like that was a reasonable trade-off for a simpler, more understandable and legible graph. And then the edges. So what we do for edges in the graph is we actually first look for variable assignments. So these are places in the graph or in the notebook where we are assigning a variable a value. And then we look for references to those variables. And we generate a directed edge from every assignment to every reference of that same variable. So to answer the obvious question here, how do we do that? Yes, we are parsing the code directly, and we are parsing it live as you're editing the notebook. This is actually, fortunately, pretty well understood in kind of the programming languages and compilers community, and there's like a whole other talk that you could do about how you actually do this. But for the purposes of this transformation, the only concept that we actually really need is the abstract syntax tree. And Python is really nice because Python actually has a library for generating this data structure automatically for you. And so all we're doing here is generating a semantic representation of what the code is supposed to do before we actually go and run it. If you were a Python interpreter or a compiler, you would then actually go run the code. For us, we actually just look at this tree. And as I said before, we were looking for assignments and we were looking for references, which you can see quite clearly here. We have the assignments right here in these assigned nodes, and then the references kind of down here in the named nodes. Cool. So we have a graph. We can create a graph from a notebook. We're all done, right? Good. There's actually a couple issues with the approach that I just described, and I'm wondering if people have spotted the problems. OK, no volunteers. I got one.
How do you avoid confusion or I guess,
It's actually a really good question. And that's something that I can talk about in sort of like the usability section later. But actually the biggest problem here is that this does not generate a DAG. You can have cycles. There's no restriction on notebooks that doesn't, disallows this. And so if you just naively try to do the transformation I just described, you can end up with a cycle between cells. And then the other big problem is that sibling nodes in the graph, you can have sibling nodes in the graph where the ordering actually really matters. And their DAGs just have no opinion on which way to run these nodes. So if you could potentially rerun it and get different results every time. Fortunately, there's actually a fairly simple and elegant solution to this, which is that we combine sort of the traditional linearity of notebooks with the DAG structure to basically be a tiebreaker. So in the case of a cycle, all we do is we remove sort of the backwards edge, and that's nice. And in the case of sibling nodes, we strictly order them based on the order that they appear in the notebook. May not be what you wanted sometimes, but it does produce consistent ordering. And actually, we've had this in production for months with thousands of people pressure testing it. And what we found is that actually, like, the vast majority of the time, this is a really good heuristic, even though you can maybe come up with some edge cases where it's not precisely what you were expecting. OK, so at this point, I'm going to put it all together. I'm talk about how we actually implemented this on top of IPython. The last concept that I need to introduce here in order to fully flesh this out is the idea of staleness. This is really, really straightforward. It's just cells that are currently out of sync with the notebook. So a cell is stale if it hasn't been run yet in this kernel session. So if you've restarted the kernel and the cell hasn't been run, it's out of sync with the memory. If an upstream cell has been edited, obviously the cell is no longer up to date. Interestingly, if an upstream cell has been run, all of its downstream cells are also stale because cells may not produce the same result every time. Think about randomness or data just updating. And then lastly, if any upstream cell of this cell has itself become stale, we have to propagate that all the way through. So with that, the algorithm. So on each edit, we run each cell through the ASD, and we compute sort of these inputs and output variables, as we call them in Hex. Then we recompute the DAG based on that. So then we traverse all of the cells upstream and downstream. And it's worth noting that sometimes upstream cells need to be rerun as well as downstream cells. Upstream, if anything's up to date, filter that out. Downstream, we mark everything as stale. And then we queue all of these cell runs into the kernel sort of in order, in the notebook order automatically. And we're just running these in the regular IPython kernel. And then we mark each cell as up to date after it runs successfully. You mentioned usability earlier. We did have to do a bunch of work on the usability side. It was actually probably one of the hardest things that we did as part of this whole project. And there was a few main things that we implemented on the usability front. So one is it's really common for notebooks to have the first cell here be just a bunch of import statements. And so this rarely ever changes. But it also has creates dependencies on literally every other cell in the notebook, which when you're sort of thinking about this DAG UI can create a lot of clutter. So we actually hide import edges by default. Another one is we also by default hide cells with no links. These are often just markdown cells, which are really important for the narrative, but much less important for the data flow of the notebook. And then lastly, if there's two edges between two nodes, we merge them into a single edge just to kind of reduce clutter. I mean, that's pretty much it end to end. I've left out a ton of stuff, obviously, on the implementation side. On the usability, I mentioned usability testing and making sure that it was understandable to people kind of coming in and they actually could really operate with it and figure out what was going on. There was a big old migration that we had to do to get all the notebooks into the new format. But overall, this has been just a phenomenally successful project, I think. I mean, it's one of the things that I hear a lot about when people start using Hex. They're like, I'm just never going back to the old way. And that, for me personally, I built a lot of data products, and I don't know, hearing things like that just means that I'm doing my job right, I think. Lots of stuff we could do in the future. I'm really excited sort of about the future of where we can take notebook compute. You could talk about, better isolation between cells, doing things with lambdas, caching, other parallelization and performance improvements. There's really just a whole universe of stuff that this opens up. And we're going to continue to explore that at Hex and see what we can build for you all. So yeah. There we go. And of course, I would be completely remiss if I did not mention the incredibly talented team that put all this together for you. I'm standing up here and I get to take all the credit, but actually it was these really, really wonderful folks who did a lot of sort of the design and the inventing and all the legwork of making it a reality. And I personally couldn't be more thrilled to work with this incredible group of engineers. And if you too are interested in working on this stuff, I feel obligated to mention that we are hiring for a bunch of different roles, and you can come find me at the conference if you want to talk more about that. So yeah, that's it for me. Thanks for all coming.